The next section is on retirement savings, and we're going to really focus on the mathematics of what we call an annuity. Now, an annuity is an account much like a retirement account where money is put into it over time, often on a monthly or yearly basis. And over time, that account will grow. And in addition to continuously depositing money into this account, it will also gain interest, much like a compound interest formula, where over time it will grow. As we kind of talked about before. Now, the difference here is that instead of putting up a lump sum up front and then seeing what will happen as it grows over interest, which is what the compound interest formula does, in this case, we're continuously putting money in time after time after time after time, and seeing how that grows. Now, this is a little bit more of a complex interaction because each one of those deposits will grow based on compound interest. So what you could do is each individual payment figure out, well, how much money will that accrue over time? The difference is each payment is paid off at like is put into that account at a different point in time, which means it has a different amount of interest accrued. And the math gets a little bit more complicated here. It turns out that there's actually a really simple formula for determining the future value of an annuity, which is built upon what we call the geometric series sum. Um, Instead of, we're not going to really dive into the mathematics of why these formulas are true because it would take a lot of time that we really don't have. But I just wanted to show you how we can calculate these values and kind of explore what an annuity is and how that applies to retirement savings. And one other thing I wanted to mention before we actually get into the math here is that 10.4 did not used to be in the book, so this section is not in my initial packet. There's actually a separate little mini packet that just a single page of notes, which I will be posting below this video if you would like to find it. So it's not in the other packet, just because we didn't used to go into this, and actually usually I just skip this section. Not that it's not important, but usually because we have enough other things going on. But just because you will have a little bit of homework on this, I wanted to at least cover the basics of annuities. Um, and also I wanted to mention that in our book, they only get into the annual case, but in my lecture here, I'm going to do two different cases. One, talk about an annual annuity where payments are put in once per year, but also talk about what if it's happening every month, because this is a little bit more of a standard type of annuity. Most of the time when people have a retirement account, usually what will happen is they take a portion of their paycheck and automatically deposit that into their retirement savings. And that's going to be done on a monthly basis, not on an annual basis. The math is very similar, and just like we covered before when we were in talking about compound interest, the only really difference here is the difference between annual compounding and monthly compounding. Um, and otherwise, the difference in the formulas, as you can see from the formulas, they're very similar. But anyways, let's get into, let's look at an example and just talk about the future value of an annuity. And also when we refer to future value, what we're going to be calculating is once we are done putting all this money into it over a fixed period of time, how much will we have at the end? You can also do mathematics of other components like what we call present value and stuff, but again, we're not going to get into any of those other parts. So let's look at the first example. It says find the future value of an annuity where Lucia deposits $2,400 per month for 10 years when compounded yearly. And sorry, I read that wrong. She deposits $2,400 per year for 10 years compounded yearly at a rate of 3%. So we can imagine at the first year, she's putting in $2,400. Then the next year, $2,400, and so on and so on and so forth. And if we didn't know how interest work, we could say, well, that's 10 payments or 10 investments of $2,400. So she would have $24,000 at the end of 10 years, assuming she was not getting any interest. But then the question is, how does interest apply to that? And common sense would dictate, well, the first payment is going to get the full length of interest, but each subsequent payment, since those are made later, will get less and less interest because they have had less time to accrue over that period of time. So you can kind of think of it as a timeline: $2,400, $2,400, $2,400, 24, 2,400, 2,400, and so on. Each one of those is growing, but the one that happened first, the first payment, had a much longer time for interest to grow than the later payments. But at the end of the day, that's kind of the nature of the mathematics of annuities. But luckily, we could just use the formula provided to figure out what is the future value of an annuity when payments are made on an annual basis. And if you look in the book, this is the exact same formula. I did use a little bit of different variables because I'm trying to be consistent with the variables that I used throughout the compound interest examples from 10.1 to 10.3. But basically here the F stands for the future value of the annuity. Basically, how much money will Lucia have in her retirement account after those 10 years? C stands for her annual contribution, so how much is she putting in, which is 2,400 in this case. R stands for the interest rate, and T stands for the time in years, just as they were in the last set of videos. And we have all that information. Obviously, we need to know how much is she putting in C. Time frame is 10 years, so we could go ahead and note that little t is equal to 10. The annual contribution is $2,400, and then the interest rate, the APR, is 3%, which is R. And remember, we want to plug that in as a decimal into these formulas, as we do typically with almost every formula involving interest rates or percentages. Anyways, if we plug all that in, let's go ahead and just see what will happen. The future value of her annuity will be the annual contribution, 2,400, multiplied by, and I put it all in brackets just to sort of, you don't necessarily have to use a bracket, but basically we want to make sure that that contribution is multiplied by this larger fraction. A lot of times in financial textbooks, this whole fraction will be described as a singular term pertaining to the annuity with a particular interest rate and time. But anyways, in this case, we have 1 plus r in the parentheses, which would be 1 plus 0.03. That's going to be 1.03 raised to the power of the time frame, which is 10 years, minus 1 divided by just r by itself. So plugging all that in would leave us with this. And again, a question you may be wondering is, well, why does this formula work? Why does this make any sort of sense? And that's something that I'm not going to really get into in these videos, but actually on my YouTube channel, I did get into the mathematics of annuities and all finance in another class of mine, Math 1053. And if you really want to dive into that, that's a different lecture series you could go into. But time is very limited, right? It's the last week of class. I'm not going to necessarily expect you guys to take that deep of a dive into this sort of math. What I think is more important is can we figure it out? Can we analyze what's happening? We don't necessarily need to know the how and why, but just know that there is a pattern behind these transactions, and that's the essence of this formula. Anyways, let's go ahead and type this all into our calculator to see what we're looking at. So we've got $2,400 multiplied by, and how I'm going to do it is I'm just going to type in the numerator in parentheses, whoops, minus 1, and then I'm going to divide it by the denominator, also in parentheses. But one thing that I recommend is be very careful with your parentheses here, and try doing these calculations with your own calculator, because in my experience, students often have a little bit of trouble with these slightly more complicated finance transactions. And if you're not getting the same answers as me, we'll try to figure out why that's the case. Like, what's happening in your calculator that is going wrong? Is it the order of operations? Is something, something off here? But anyways, what we come up with is the future value of our annuity, or another word for another way of describing a retirement savings account, is $27,513 and 31 cents. And as I said before, I think remember that with finance we're rounding to the nearest cent, the nearest hundredth, typically because we don't have a digit beyond the cent for money. Anyways, what that would leave us with is about $27,000 after all is said and done. And notably, it should be more than the baseline. Right, like I said, well, if I'm doing 10 payments of $2,400, that would be $24,000 without interest. So we can kind of see, well, how much interest have we gotten from this as an idea and kind of compare. But the future value should be more, and it should be fairly close. In this case, there is a 3% interest rate, but you don't just apply 3% to it. That's, because of the idea I'm trying to convey here is the complexity of when the deposits are made and how that affects the interest that's accrued over the timeline. Is what is a little bit more complicated. And in the next one, we'll look at what is a case in which it is compounded monthly instead, and if it was to be done monthly. But in our book, they're all done yearly. So I think that your homework will only ask you yearly cases, which means that you really only need to worry about this formula. But I do want to discuss, a more realistic scenario when it is done monthly, because I do feel like this is probably more of a common type of annuity you could be dealing with in your actual lives.